So, welcome to Life Station 8. What we will do today? So, we will go through something called hardenability. Right? So, um, not hardenability, sorry, my mistake. So, we'll go through something called weldability. So, we'll briefly uh, talk about what is weldability. In general, we will talk about what factors will affect your weldability of your structure. And then afterwards, maybe we will classify in the sense depending on different materials. uh, it can be soft metals, it can be hard metals, depending on different kinds of metals, how the weldability will vary. So for today's session, this will be a overall view of weldability, and we will try to understand what are the different factors in terms of uh, material properties, in terms of material properties, physical properties, elastic properties. So different kind of material properties, how they will affect my weldability, right? Elastic property. So we will go through them one by one. So initially to start with, uh, let's talk about, let's try to define what is weldability, right? So what is weldability? Any answer from your side? So weldability will refer to the ease with which a material can be welded, right, to produce some sound defect-free weld with acceptable uh, material property. So it can be mechanical property, it can be thermal property, electrical property. So we will characterize my joints, right? So this is ease of or ease with which material can be welded to produce sound defect-free joints. Now, what are the key factors which will affect my weldability? I will, of course, explain one by one, but in general, there are few factors which I want to note it down. So, I will tell this as key factors affecting weldability. What are those? So, I can have some alloying element. Let's say you are alloying to different composition or different metals, right? So let's say some elements like chromium or nickel or molybdenum. So these kind of elements can affect your weldability. For example, if you see steels, alloy steels, that may require special welding techniques due to some hardening behavior or there are some inherent brittleness in highly alloyed steel if you are mixing chromium or nickel or molybdenum, this kind of elements. So they will greatly affect your weldability of the structure. Then there is something, some thermal properties like thermal conductivity or thermal expansion coefficient. Right? What else? Melting point. Melting point also can affect your weldability. I will come to that. So I will come one by one. Then you can have a residual stress in your structure that can also affect your weldability. Right? Then hardness or ductility of your structure. So those are all things, even the geometry of the joint. So or this joint design or geometry, joint design or geometry, or mainly the thickness. So thickness of the metal will greatly affect your weldability of the structure. So thickness. So these all will affect my weldability. I will try to explain one by one. Right now, yeah. And one more thing, uh, your weldability of your structure will depend on, uh, you can classify in some other sense. So it can be influenced by, I will note it down, weldability can be influenced by, what are those things? So it can be influenced by the steps which you are by the steps which you are following in your welding procedure. So steps followed in welding procedure, basically the welding cycle, right? So how much heat you are generating, for how much time, what is my cooling rate, those aspects will affect my weldability of its structure. So steps followed in welding, this will affect my weldability. Then what is the purpose? So what is my purpose to join those metals? That also will affect my weldability. And fabrication condition. So these are few factors. Fabrication condition, right? So, so welding of a metal, let's say you are welding some uh, metal like aluminum. Okay, so you are welding some metal like, I'll take this. Is it easy to weld with shielded metal arc welding or not? Aluminum metal. Hmm. So if you
Yes,
see
sir. It's
uh,
aluminium is high electrical conductivity,
high electrical conductivity, okay,
but low melting point.
yes,
So I
that is
think it
true.
can be easily welded.
So the thing is, depending on your technique. So let's say at one case you are using shielded metal arc welding for one case, and for another case you are using some TIG or MIG welding. Now, aluminum is having some affinity with oxide formation, right? It can easily form oxide. It can easily form oxide. Now, the protection or coating or whatever thing you use in welding, that is not as effective as what you do in TIG or MIG. So, for shielded metal arc welding, the protection of the weld pool is not that much effective compared to TIG or MIG. So, SMAW, with SMAW, aluminum weldability is less. Rather, for the same metal with TIG or MIG, aluminum is easily weldable. Got my point? Similarly, if you, let's say you are joining steel metal. So steel weld joint may perform well under some normal atmospheric condition, but the same metal, it may exhibit some very poor toughness or poor ductility at some sub-zero temperature condition. So depending on your, what is your welding condition, what is your processing condition, depending on those, for the same metal, my weldability can vary, right? Now, I was talking about those steps of the welding procedure. What kind of steps I was talking about? So, if I am talking about steps in welding procedure, which will affect my weldability, steps in welding procedure, I mean to say that, uh, so you can have some steps like surface or edge preparation. So you may need to use some kind of edge preparation or surface preparation technique to have some easy weldability of the metal. So again, I will note it down. So you can have surface or edge preparation. Then you can have some uh, pre or post heating weld treatment, pre or post weld heat treatment. Then you can have some welding parameters. I'm not going to that. Can you tell me why post weld heat treatment uh, can be beneficial in welding, even pre weld, pre heating of your metal? So post-well heat treatment mainly is used to relieve my residual stress, right? I was talking about that stress relief annealing. So mainly this is beneficial for reduction in residual stress, right? So whenever you will reduce your residual stress, that will automatically will influence your weldability of your metal, enough. So
Yes.
yeah. So initially to start with, uh, we'll start something from weldability of metals by fusion welding process. So there are different welding techniques like fusion welding, solid state welding, those things. So initially we will start from fusion welding process. So what were the factors I was talking about? In both fusion welding or whatever welding technique you were talking about, so be it fusion, be it solid state welding, the the material properties that will affect my weldability, that will be common in nature, right? So I was talking about the chemical properties or the composition of of my metal. Mainly the composition will affect the weldability. So I will note those one by one. Composition. So how my composition will affect my weldability. Metals can have some unfavorable elements always. Whenever you have some alloying powder, or let's say you're doing some additive manufacturing of some alloy powders. So it can have some unfavorable elements like lead, like sulfur, phosphorus, some low melting temperature constituent that can also uh, increase your cracking tendency. So mainly weldability will define that your metal, the welded structure that has greater affinity or less affinity to cracking thing, right? So if you are having some unfavorable elements like lead, sulfur, phosphorus, or some low melting low melting point constituents, that will always increase my solidification cracking tendency. That will always increase my location cracking tendency with high concentration of uh, these elements. Wherever, if you are having some hardening elements, so you can also have some hardening elements. What are some hardening elements that can be present in your metal? So in steel, carbon is a hardening element, right? So if you increase the percentage of carbon, the hardness will get increased. So these were my unfavorable composition, unfavorable, unfavorable elements. Now, what are the hardening elements? So you can have carbon, you can have some tungsten, vanadium. So these are different elements which can increase your hardness. And if you increase your hardness, what kind of defect it will produce? So it will be susceptible to something called embrittlement. So more harder the material, the brittleness in the structure will get induced, right? So I want to note some. So these also I have noted from myself. So from somewhere I've got these kind of relations. So there are some empirical equations. So there are empirical equations where people have found out for easiness to understand that what will be my percentage of composition so that I can calculate my, let's say, cracking tendency. I can directly calculate the cracking tendency of a metal structure from different percentage of my composition, right? So these are empirical. Depending on experiments, they have found out, depending on their experiments, that if I add this much of percentage of this element, this much of percentage of that element, I will have some value. So they have quantified that cracking sensitivity or crack susceptibility, whatever you will say. So I want to note those down. So first is hot cracking. hot cracking sensitivity. What is hot cracking sensitivity, or how the previous researchers have equated the hot cracking sensitivity is like this. So you'll have sulfur, you'll have phosphorus. If you have some silicon in material, then you can have some nickel, this into 1000. Just remember, this is empirical in nature. This will not always be true. This is true for their experimental condition, for their uh, processing condition, and whatever they wanted to prepare. 3 manganese plus chromium plus monil plus vanadium. So what they had mentioned is, if hot cracking sensitivity is less than 4, the steel material is not sensitive to hot cracking. Depending on their calculation, they have found out if HCS is less than 4, my steel is not sensitive to hot cracking. If it is greater than 4, the probability will be more to crack, right? So steel is not sensitive to hot crack. Then there are some formula of something called unit crack susceptibility. Let's not go into much detail. So what I have done is just noted this empirical formula to understand that how they are related with different composition of your material. So next is unit unit crack susceptibility. Unit crack. And mainly they had done for shielded metal alkali, right? They had done this experiment for shielded metal alkali, and they found that unit crack susceptibility is having some relation like this: 75 P plus you can add niobium. So in their steel material, they had niobium. They also had silicon in the steel material. They also had manganese. So this is how they had obtained what will be their unit crack susceptibility for these elements, right? So that's how you can, depending on your experimental condition, you can obtain some empirical relation. Okay. Now, one more thing I want to mention: reheat cracking. So one of the researchers had obtained some prediction for reheat cracking, or how my reheat cracking tendency will be affected depending on different compositions. So this reheat cracking, its the probability of reheat cracking is related with these elements: chromium, copper, monel, vanadium, niobium, titanium, these things. Again, there is not much to understand over here, but to get some essence that yes, if there are different compositions in my material, depending on your uh, wet percentage of the composition, how much it is present, depending on that, the tendency to cracking will vary, right? I can estimate or I can quantify that um, this is more prone to cracking or there is uh, less probability of cracking tendency. So these things I can find out. That is one. So these I was talking about in terms of composition of the material. Next I will be talking on next I will be talking on affinity with atmospheric gas. So whatever parameters I'm talking right now, let's say this is B and this was A uh, composition. So whatever parameters I'm talking right now, these will be common for fusion welding, for solid state welding, but they will affect your weldability in different way, right? Now, in terms of affinity of weld metal with atmospheric gases, can you tell me the metals like, uh, let's say aluminum I was talking about, how is the affinity with gases like oxygen, nitrogen? I have already mentioned it. So they will show easy reaction, right? Easy reaction with gases like oxygen and nitrogen and some impurities by forming some compound through some chemical reaction. I don't know. Uh, so they will form some compound. So metals like aluminium, metals like magnesium, metals like titanium, preferably these three show affinity with atmospheric gases. So if I tell atmospheric gases, what are the gases? So it can be O2, it can be nitrogen, it can be other gases. Mostly we talk about oxide formation or nitride formation, even carbide formation. So most of the metals at high temperature during fusion welding, if they are not protected, I mean, if they are not protected with some flux metal, or if you're not doing your experiment in vacuum condition, they will always react with air elements like oxide and nitride formation will be there. So if not protected, they will always tend to react with these gases and they will form oxides, nitrides, sulfides, hydrides. So those all can be observed in the form of some inclusion in your weld metal, right? So uh, if not protected, these metal can have easy reaction with air and can form what they can form. They can form oxide, they can form sulfide, they can form nitride, they also can form some hydrides by reaction with hydrogen. You know? Now there are two graphs which I want to show over here. So first thing is if you are increasing if you are increasing the affinity of metals with gases by uh, not protecting your weld pool. So let's say I'm increasing the tendency of affinity of reaction, reaction of metals with gases, reaction of metals with gas, and my y-axis, if it tells me the weldability, the ease of doing welding. So I will identify it as ease of welding. So how my graph will vary? It will have a negative slope. So if this is increasing, this will go down. Got my point?
Yes, sir.
Same is true for something called solubility. So this is also a parameter. So I will mention it as C. So if gas is dissolved in your metal, uh, they will they will react in two different ways. So either they will form porosity in your structure, or uh, they will embrittle your metal, right? So if the gases are dissolved in your metals, if gases are dissolved in metals, so either they will create porosity, or they can create embrittleness, right? Now, a large difference in solubility of gases, liquid and solid state of a metal increase the possibility of porosity formation, right? Um, due to high gas entrapment tendency. So in terms of graph, so graph is more visually attractive, right? So if I plot some graph, something like this, and let's say my x-axis is difference in solubility of gases in liquid and solid state. Solid state, by telling solid state, I mean that is after solidification. By telling liquid means that is just after melting. And if this is my weldability, how it will behave? Again, it will have some kind of decreasing nature of to have some kind of decreasing nature, something like this. So more is the difference in the solubility of gases in liquid and solid state. The tendency
It's
to
belt
form, yeah, weldability
weldability is very good.
will get reduced.
Yes.
Let me have some water. Any question till now?
No, sir.
Sorry. Okay. So the next parameter is, so this will be C, and next is D. What is the next? I have talked about solubility. I have talked about composition. Let's talk about melting point. Okay, so let's talk about next melting point. How my melting point will affect my weldability of a structure. How you can determine your melting temperature, or what process parameters will uh, what process parameters will give you some idea in terms of this should be my melting temperature, or this is a high melting temperature metal, something like that. What
Sir,
parameters it can be?
high melting point required more heat
Correct.
during welding process,
Yeah.
and a low melting point consume less heat, and the impurities of allying elements affect to the melting point. If
Right.
it contains some impurities of like elements, it can be reduce the melting point of the weld
Exactly.
metals.
Exactly. So there are two three parameters which can uh, govern my melting temperature of a metal. As you were saying, there can be this high note. Yeah. So as I was saying, there can be uh, as you were saying that the heat input, net heat input will govern my melting temperature. Of course, the impurities if you have, those also will govern my melting temperature. So these two are somewhere similar. So this net heat input and power density, these two parameters are somewhat similar, and fine. So those will determine or those will govern my what is the melting temperature of a metal, right? So these parameters will greatly affect my melting temperature. Can you name some high melting point temperature metals?
Pure irons, sir.
Pure iron. Okay.
Pure iron.
Then you can
Uh,
have let you can have tungsten. You can have titanium. You can have cobalt. These are more heat resistant metals.
yes,
So
sir.
the melting point is very high. Titanium, so Fe also, tungsten, cobalt. These three are much higher than Fe, of course. But yeah, so those high melting point temperature metals, they are found more difficult to weld by fusion welding, than low melting temperature metals like aluminum, magnesium, providing other characteristics remain identical. So these are more difficult for welding compared to low melting point metals. Now, fusion welding of in between these two, medium melting temperature metals, they are found to be comparatively easier as compared to these two extremities, right? So, in low melting temperature metals, uh, they make control of weld pool difficult and sensitive for melt especially in case of some thin sections or So for low melting point metals, if you are welding some thin section, thin sheet joining, that will be much more difficult. Thin sheet joining is difficult. On the other hand, on the other hand, for high melting point metals, that impose difficulty in melting of flying surfaces. So difficulty in welding of right. Now in solid state welding, so this I was talking in terms of melting temperature, of course. So in solid state welding, that more rely on your large scale deformation, है ना? So if you are talking about friction stir, if you are talking about uh, some rolling operation, so there
ultrasonic,
ultrasonic, yeah, ultrasonic
explosive,
also, explosive also, they are more relying on large scale deformation. So there we don't talk about uh, my metal should go above melting or below melting, something like that. We talk about more strain, more stress, strain rate. These parameters we talk about in solid state welding process. Now, ease of joining in solid state welding process, what will happen? That will decrease with increase in melting temperature of parent metals. So, if your metal is having some high melting temperature, that will also inherently provide you some higher yield strength, reduced ductility, right? So the hardness of that metal will be much higher than what your aluminum or magnesium or low melting point metals are having. So in case of solid state welding process, if your melting temperature of your metal is much higher, that means the yield strength of your metal is much higher. That means the tendency or easiness of joining through by in solid state for that metal is very difficult. So metals like iron, tungsten, cobalt, these are difficult to weld with solid state welding process because of their higher yield strength or lower ductility. Right? Now again I will draw some graph, whatever I have just talked. So let's say my y-axis is melting temperature and my x-axis is weldability. Now how will it vary is something like this. Initially it will get increased and then with increase in melting temperature, something like this. So they will having some limitation on your temperature till which the weldability will get increased, and after that it will again decrease. Now in terms of different metals, I was talking about different metals, no? So let's say curve, in this curve, the highest portion, which is having the much higher weldability. So this is my melting temperature. This will have most lowest melting temperature metals, something like zinc or brass, not brass or brass. I forgot what is the melting temperature. Let me check once. Let me check once. No, brass melting temperature, of course, very high because of it is having copper in itself. Zinc is having very low melting temperature, somewhere around 300. Right? Can you name few more low melting point metals? You have tin, you have lead also. They are very low in their melting temperature. Then in this graph we can have aluminum over here. Then more you go towards uh, to this curve, my melting temperature will keep on increasing. You know,
Yes, sir.
so this was B. Now one parameter is related to this melting point, that is the range of solidification. So solidification temperature range is also important in your weldability. Solidification. So how my range of solidification will affect my weldability? First, what is solidification temperature range? What is solidification temperature range? If I'm talking about some kind of range, that must be some difference between two temperatures. What are those two temperatures? Remember in phase diagram, in binary alloy phase diagram, uh, even in, if you refer iron carbon phase diagram, there were some curves like this, some kind of curve like this, right? What were those curves? What is this curve? This is called liquidus line. So any kind of alloy will not melt at a single temperature. What it will have, it will melt or solidify over a range of temperature. I will have some range of temperature. Now this is my liquidus line, which dictates me above this line, everything will be in liquid state, right? Now This is my, sorry, this is, what is this? This is solidus line. What is it saying, solidus line? So across here, these regions, these are in all solid state. These are all in solid state. Of course, there will be have some phase transformation in your structure. I'm not going into that direction. So as of now, I am talking about the range of temperature. So there will be a range of temperature through which my melt will get solidified, right? Depending on your composition also. So this is my composition. Depending on what is your composition in your metal alloy, your solidification temperature range will also change. What is this region called, this red hashed line, this region? What is this called? So if over this everything is liquid and below this everything is solid, what will happen over here? It is called mushy zone. Liquid and solid will coexist, right? What is this point called? This red dotted point. So let's say you are having some liquid over here, and at a single temperature, this is a single temperature where you are transforming your liquid to solids. So if you are talking about composition, binary alloy, you are having two different metals. So from liquid, I will convert it to two different metals. What is this point called? This is called
Eutectic.
eutectic point. Right, right. So this is my solidification temperature range, the difference of solidus and liquidus temperature. So this is the difference of solidus and liquidus temperature. If my solidification temperature range is much higher, let's say this is uh, higher than 50 degree, that will increase the cracking tendency or that will decrease my cracking tendency. Any kind of cracking, it can be solidification cracking, it can be liquefaction cracking. So those two different cracking I have talked about in my previous lecture. So if my solidification temperature range is much higher, it will increase my cracking tendency, right? So metals, so pure metals, or the eutectic composition, I was talking about this eutectic composition. So let me note it down. Pure metals or eutectic compositions. What did I tell for eutectic composition? That will solidify at a single temperature. There will be no range of temperature where they will solidify, right? So
Yes.
at a fixed temperature. Solidification is done at a fixed temperature. Solidification is done. Basically, if you're having a narrow solidification temperature range, they will exhibit limited cracking tendency, right? So, if I increase my solidification temperature range, I will decrease my weldability. Not exactly linear, of course, it will have some something like this. So, what will be the highest weldable range of solidification? So, that will be a pure metal or some eutectic alloy as I was talking about. So, this point will be dictating pure metal or eutectic, and this will be dictating alloys other than eutectic. Question. Okay. So we have talked about melting point, and then we have talked about this solidification temperature. Next, we can come to the parameters like thermal properties of your metal. So depending on your thermal properties also, your weldability will vary a lot. So what was my E? So this was E. And then I will have F. So I will be talking about thermal properties. And in thermal properties, we have two different things. What are those? I will have thermal conductivity of the metal and thermal expansion coefficient. So what is thermal conductivity? What it will tell me? The thermal conductivity of a metal. It will determine how far or how fast the heat will be dissipated from the weld pool to the base metal during fusion welding. If you're talking about fusion welding, so from the weld pool to the base metal, there will be heat dissipation. So how far the heat is getting dissipated, how fast or how slow the heat is getting dissipated, those things will be governed by something called thermal conductivity of my metal. Right? So my thermal conductivity will also affect the net heat input requirement for the fusion welding. So that will affect my uh, melt pool size. That will affect my melt pool shape also. In general, if you see the metals which are highly conductive in nature, that will require more heat input or less heat input.
Yes, sir. Please repeat question again.
So if you are having high thermal conductivity, the metal is having high thermal conductivity. For welding, do you need more heat input or less heat input?
less heat input, high thermal conductivity.
So if your metal is having high thermal conductivity, it can dissipate heat very easily. It can cool down faster. So let's say you are joining two copper metal. You are joining two copper, something like this. I am using uh, I am using same not same. What I mean to say, copper will cool down faster by the time you go till the melting temperature. So your requirement for the heat input need to be higher there compared to if you are, let's say, welding some steel metal. There it cannot dissipate heat quickly. It will store the heat. It will soak up the heat. You know? So the heat input requirement will be less there. So thermal conductivity higher, heat input also will be higher. Got my point? So if you try to draw some schematic, if you try to draw some schematic in terms of the pool size, melt pool size, so it will be something like this. For highly conductive metals, for highly conductive metals, the region, the fusion region where it is getting melted, that will be limited. But the heat affected region, that will be large enough because of higher heat dissipation. So this is my fusion zone. This is my heat affected zone. And this I am talking about thermal conductivity is higher compared to that. If I am talking about low thermally conductive metals, in low thermally conductive metals, my fusion region will be high enough. And the heat affected zone will be less over there because of less heat dissipation. Got my point? So this is for heat affected zone. This is fusion zone. This is heat affected zone. And over here I'm talking about correct. So my thermal conductivity will increase if this is my thermal conductivity. If that is getting increased, and this is weldability with increase in thermal conductivity, that will go down. Okay. Now, if that was the condition for thermal conductivity, now if you want to try to look at in terms of thermal expansion question, do I have any space? Yeah, we have space. So if you want to look at the property like thermal expansion coefficient, first, what is thermal expansion coefficient? So how it will expand with temperature, right? So uh, I believe you remember this equation, um, E alpha delta T. So if there is no external load, if you are applying only temperature, my thermal stress that will get induced in your structure, that will depend on what is my temperature gradient or what is the rise in temperature and the thermal expansion coefficient. E is Young's modulus, of course. My material is, let's say, that is in elastic state, I am assuming. So alpha delta is my thermal strain, E alpha delta will be my thermal stress. So my thermal expansion coefficient of metal will affect what? Residual stress and distortion tendency of your weld joint, right? That is my the main parameter that will govern me to to the condition of to the condition of your residual stress is uh, very high or no. Your residual stress is tensile in nature or compressive. Those things. So that aspect we have covered in our earlier lecture, right? So this will affect my residual stress and distortion. So if you are increasing in thermal expansion coefficient, what that will do? That will increase my localized expansion and contraction, right? That which will be experienced by your parent metal during fusion welding. And if it is experiencing that localized stress in terms of expansion and contraction, that will increase the residual stress under identical welding condition, whatever the welding condition it is. Let's say uh, for copper and aluminum. Copper and aluminum are having different expansion coefficient, or copper and Fe. Those are having different expansion coefficient. Depending on what is experiencing more expansion, there will those residual stress will be getting generated, right? So whenever your metal is having higher thermal expansion coefficient, that will show greater residual stress tendency or distortion tendency as compared to metals like uh, which are having low coefficient of expansion, like mild steel. Mild steel is having low coefficient of expansion. Okay, so yeah, again I will draw some graphs. So for low expansion coefficient metals, if you see the residual stress in your welded structure, let's say my welded structure is something like this. Here I have done welding in the middle. Right? So whatever stress I will show as of now, in the middle I will having tensile residual stress, and away from that weld center line I will having compressive residual stress. As simple as that. So for low expansion coefficient metals, I will have something like this. For high expansion coefficient, this should be smaller compared to this. Got it? So this is tensile. These things we have discussed. This is compressive. And what will happen if you increase this alpha value? The residual stress will get increased. Any questions?
No, sir.
Okay. So once you are done with this thermal property, then comes your structural properties. So what structural properties I was talking about? I was talking about yield strength of your metal. So that will also affect your weldability. So for fusion welding of a metal, that is not directly affected by your yield strength, but uh, yes, that will affect to some extent. So the residual stress, what we are talking about, that also depend on your yield strength of your weld metal. Hmm. So yeah, and one more thing I want to mention over here in autogeneous welding. So in autogeneous welding or welding where you are using some filler metals or electrode kind of thing, of course, that results in maximum residual stress approximately similar to the base metal yield strength. So that will cause in many issues related with cracking of weld metal in the heat effective zone. So the low yield strength filler electrode like uh, nickel, nickel is a low yield strength filler. So that is sometimes intentionally selected for fusion welding of some high hardenable metals like cast iron. Cast iron is very hard in nature. So yeah, that is one thing. So I must note it down. So I was talking about note low yield strength filler or electrode. So nickel is an example of that. Is intentionally selected for fusion welding of hard metals. This is same for yield strength also. Sigma yield. If I increase my yield strength, my residual stress also gets increased. Okay. I'll come to few more parameters. So there are some geometrical parameters or thickness. So basically, thickness will also affect your weldability, and if time permits, then I will come to this solid state part, how that will affect the weldability. And before that, let's uh, let's have those quick question and answer MCQ things. Let's go through those. I believe this discussion will be fine enough to answer this question. So, austenitic stainless steel offers lower weldability than mild steel for fusion welding due to what? So, in terms of malleability, there is no difference in terms of stainless steel and mild steel. They have some difference in thermal conductivity. Because they are having difference in thermal conductivity, they will have, not because of that, they will also having some difference in thermal expansion coefficient. So that is the parameter which will govern the weldability of these two structures. Okay. So my right option is option C. If you
Yes,
have any,
sir.
yeah, okay. If you have any confusion, please raise the concern. So weldability of any metal system is defined on the basis of what? This also
All
will
of
have
the
all of this. Fine. So welding process, application requirement, the condition of welding process, all will affect my weldability of the structure. This is a little bit diverting from this today's discussion, but anyhow,
0.2 to 0.5%.
there. So that is my medium carbon steel type of residual stress in welding zone changes from compressive to tensile.
End of solidification.
Yeah. Weldability of a metal depends on.
All of these.
Mhm. Okay. Yeah. As of now, we have not talked about something on this IMC formation, uh, size and shape of grains. But anyhow, in our previous discussion, we have talked about what this fine grain and coarse grains will affect in your weldability. Any idea on IMC formation or what is intermetallic structure? Hmm? Any idea is there? What is intermetallic
No,
structure?
no, sir.
Okay. So, intermetallic structures are, you can think it of some kind of alloying, but this is not exactly some alloy composition. So they are distinct class of materials. So they form by two or more metallic elements. So if you see in solid solution or simple metal alloys, their atoms of one metal dissolve in another in varying proportion, right? But intermetallics, they have a definite stoichiometric composition, typically form some order crystal structure. Okay? That is the main difference in terms of IMC. Uh, that is the main difference between IMC and alloy composition. Let me write it down. What I was talking for alloy, atoms of one metal that will dissolve in another in varying proportion. The composition we talk about. So dissolution is there. What is there for IMC? That will have some stoichiometric composition, typically forming a ordered crystal structure. So what crystal structures will have? They will have some specific atomic arrangement, you know, and depending on those arrangements, they will have some unique mechanical property. They will have some different thermal property. So it all depends on their distinct bonding and structural characteristics. So they will have IMC, they will have ordered crystal structure. They will have definite symmetry in composition. They can have different bonding characteristics. They either can have metallic or covalent or ionic character. Uh, in terms of melting point, because you are having some intermetallic formation, they will always have high melting points compared to the parent metals. So let's say you are mixing aluminum and copper, because I work in aluminum copper system, so I know uh, what are different IMC formations are there. So trust me. So for aluminum and copper, let's stick to this alloy system, not alloy system, this phases. So there are different IMC formation like Al2Cu, AlCu, Al4Cu9, AlCu3, depending on different proportions of copper and aluminum, depending on how fast they are diffusing in one another, right? Depending on their cross diffusion. So diffusion coefficient again will also matter. Let's not divert very much. So these will be my intermetallic compounds that may form depending on your process conditions, of course, that may form. All of those intermetallics are having higher melting points. Next is brittleness. That is another important property. So in a welding structure, I want to have the intermetallic compounds as low as possible. So intermetallic compounds are mostly brittle in nature. That will limit your, of course, the ductility, toughness of your joint. Why those brittleness are there? Because of crystalline structure. You are having order structure. If you are having order structure, that will restrict the movement of dislocation, that will typically allow deformation in metals, right? So that is there, brittleness is there. Then you can have um, thermal resistance, low electrical conductance. So those are there. So these I was talking for aluminum copper. For nickel aluminum, there are some other intermediate. You can go through this if you have some interest. So there are Ni3Al, NiAl, these kind of intermetallic formation. For titanium aluminum, there are intermetallic phases like Ti3Al, TiAl. These all are coming from phase diagram. Okay. So yeah, these are there. Okay. Where were we? So all of this, fine. Next, heat affected zone of a metallic weld joint. Let's do the question and answers for today. Uh, yeah, heat affected zone of a metallic weld joint is not affected if strengthened by this mechanisms. Any guess? Any kind of guess?
Dark hardening.
The correct answer over here is solid solution strengthening and dispersion hardening is not affected. Okay. Now, why so? So, heat affected zone of a metallic weld joint can still be affected by these kind of mechanisms, but the possibility of happening so is very less. What is solid solution strengthening? So, solid solution strengthening that occurs when some kind of alloying elements that will be dissolved in the base metals crystal structure. You know? So, uh, if I want to dissolve any kind of alloying elements in some other base metal crystal structure, that will create some kind of distortion. If it is creating a distortion, I mean, if you are trying to dissolve something, it will of course distort, right? That is common sense. And if it is creating distortion, there that will restrict the dislocation movement, right? And if it is restricting the dislocation movement, my strength and hardness will get increased. You know? Now, whenever you are doing welding, you are doing some localized heating, right? So somewhere in that region, you are fusing the material, you are going above melting temperature. But what happens to heat affected zone? There, the melting temperature is not reaching, right? There's some that is somewhere below the melting temperature, and that will be very localized region. And because of that, what will happen? That will cause some redistribution of these alloying elements. So whenever it will redistribute these alloying elements, they will reduce the effectiveness of solid solution strengthening in that zone. Basically, why heat affected zone will be affected? Because of those thermal cycles. So your heat affected zone will experience rapid heating and cooling. That will alter your microstructure, and that will potentially you will come to some kind of strengthening mechanisms, right? So in heat affected zone, the most common strengthening mechanism is the precipitation hardening and strain hardening. That is the common mechanism happen in heat affected zone. Okay. Now, what is dispersion strengthening? Uh, also don't know that. Uh, Dispersion strengthening possibly. So basically, by the name, what I can understand is that will involve some distribution of uh, fine or stable particles throughout the matrix. So if you are having those particles, that will act as obstacles to dislocation motion, and that will increase the material strength. So in heat affected zone, you're having high temperature during welding, so that will lead to coarsening. So the grain structure will get coarsened and will have partial dissolution of those particles, and the ability to impede dislocation movement, that will be less over there in heat affected zone. So yeah, these two are not the correct strengthening mechanism that will govern the strength in your heat affected zone. The most common thing is precipitation hardening and strain hardening, right? Okay. What is the driving force for the new grains in work hardenable metals through recrystallization? What is recrystallization? What is recrystallization? Recrystallization, uh, so basically you are replacing some deformed grains, some strained grains by a new set of strain-free grains, right? So this typically happens when your metal is heated above its recrystallization temperature, and that to depend on the material and its mechanical history by how much deformation you have done over there. So what do you need for recrystallization? You need some strain energy. More you deform the metal, more strain energy will be stored by uh, by creating some subgrain formation, by doing some uh, by breaking those grains. Okay, and it will increase your stored energy, and that will drive your uh, tendency to do those recrystallization. Are you getting my point?
Release, I think released strain energy.
So yeah, for releasing strain energy, you need to store the strain energy. If you do not have strain energy, if you do not have much higher strain energy, how the grains will have some tendency to release those energies. So it's kind of every action is its opposite reaction. If you are stored something in a high volume, then you can release those energies. Until and unless, how can you do that? I know. So for recrystallization to happen, as you were saying, in recrystallization, you will release strain energy. You have to store that strain energy in some form, and those forms are the deformation based process. More you deform the metal, more you increase the strain energy your structure, more will be the possibility of happening recrystallization, right?
Yes, sir.
So 7 is A. The driving force is stored strain energy. Hmm. Again, of course, higher weldability of carbon steel attained by preheating during fusion welding is due to, if I do preheating, as you know, that will decrease residual stress. If I do preheating, this is also common since there will be heat input requirement will be less.
All of these, sir.
All of this. Question 9. This I'll not explain. So, more time you expose any metal to a higher temperature, it will coarsen your grain size, right? As simple as that. That will increase my grain size. Agreed, no?
Yes, sir.
So then next plus strength of cold work brass at recrystallization temperature during annealing. If you are doing recrystallization, there will be a sharp drop in your strength because those will be strain-free grains. If your grains are strain-free, your toughness is much higher, your ductility is higher, not the strength.
Yes, sir.
Okay, okay. So we have some time.
Sir, today is sufficient.
Fine. Okay.
Okay, sir. Thank you, sir.
Okay. Chalo. Bye.